all of you to the Department of HST's Heritage Lecture Series. We have with us today Bharat Rao, a cryptographer, who's proposed a decipherment of the Indus Valley script, and without much further ado, it's over to the speaker. Yajnadevam has a master's in computer science from Syracuse University, and he's been working in he was working formerly with GE and then with Motorola Labs. Right now he is a self-employed professional working in the area of cryptography, and it's over to Bharat.
Yes, thank you. I have my I'd like to thank Mr. Mohan Raghavan for inviting me to give this talk. Thank you, IIT Hyderabad and the Heritage Series. So this work of mine has been going on for a couple of years, and it is related to the Indus Valley and the Indus Valley script. Just by a show of hands, how many people are familiar with the Indus Valley Civilization? Almost everybody, right? How many of you know there is a script in the Indus Valley Civilization? Half of you, okay, that's pretty good. So when there is a script and when there is an unknown script, there is always a curiosity as to what it says, and this, even if it's a simple puzzle on a newspaper or it's in an ancient inscription. So there have always been people who have been trying to solve these unknown writings that they can look at the symbols, it looks like writing, but they don't know what it says, so they will try to solve it. The famous decipherments that everyone knows of is Champignon's decipherment of the Egyptian hieroglyphs. It took him 2 years. It was not accepted until after his death. In general, most scripts were deciphered using a bilingual or trilingual inscription that came to be known that came to be referred to as the first trilingual inscription that helped crack the Egyptian hieroglyphs, the Rosetta Stone. So people ask, hey, is there a Rosetta Stone for this script or not? And there was a script called Linear P that was deciphered by someone named Michael Ventris. Michael Ventris was an outsider, he was not an archaeologist or anything like that, but he was able to crack it without a Rosetta Stone. So how can you crack something without a Rosetta Stone? There are many scripts or codexes later that were deciphered using cryptography. Famous ones are ones like Copiale cipher, recently the Zodiac cipher, and so on. And also the ciphers of Queen Mary of Scots was deciphered by people who spied on her letters, got enough information, got enough text that they could decipher it. So let us just look at how this happens in real life. There are websites that obviously do this. There are newspapers that publish cryptograms that people solve every day. Roughly 100 million cryptograms have been created and solved by ordinary people like you. So it is not something that requires any kind of special skill. It requires a little bit of patience and aptitude for problem solving. So on this website here, there are many famous speeches. We'll pick one, and you can pick anyone and you can try this at home. It will work the same way because the software that does the decipherment is essentially well known, the algorithms are well known. So let's pick, this is the Queen Elizabeth I. Let us pick a bunch of her speech, and we will copy it into this website, clip The U and I are flipped in the second part, and you paste it here, and we can just scramble it. So when you scramble it, I don't know if you can see it. Let me try to zoom into the text here. So when you scramble it, it just assigns a different value for that same letter. Okay, and once it's scrambled, this is the cryptogram. So now you have a message where you have symbols that do not have a known value, but they have a legal value. Okay, so you can solve it in different ways. One is a statistical, which is if you know the frequency of the letters, you can use that. The other is dictionary, which is what we use for Indus script. So let's solve it with the dictionary method, and it solves it. As you can see, it's the same thing. Okay, so it's pretty straightforward. So now let us try something else. Let us take this and take it to a different website. So this is a different website, and we will try to solve it and see what it does. And you can see it has figured it out. It has figured out V equal to L, C is E, M is T, and so on. It's a very simple process. We'll go through the mathematics of it. But we have something that is, we have some interesting options here. Instead of English, what happens if we choose some other language? Is it readable? Is a unknown inscription readable in more than one language? We can try to see it. Of course, we can choose any language, but if we choose something closer, like say German, if we have German here, I don't see German. Okay.
Deutsch.
Yeah. Oh, okay. Deutsch is German. Yes. Then we can see if it can solve it, and it cannot solve it. Those patterns don't even exist. Those patterns of words don't even exist. So this is a kind of commonly asked questions. Oh, you decipher it as this language. Can someone else decipher it as a different language? And the answer is no, if the length exceeds a certain amount. Okay. So we'll try something else also. Let us scramble it some more. So I've scrambled it again. I've scrambled the scrambled thing, and I'm going to re-scramble it, and I'm going to re-scramble it. So now this is more scrambled than scrambled eggs in the canteen. Okay. So I want to ask the audience: do you think if I try to solve it here, is it going to be able to solve it or not? I get one. Okay. People who say yes, raise your hand. 1, 2, 3, 4. Okay, 5. People who think, okay, 6. How many of you think it cannot solve it? 1. Come on, guys, you make a choice. 2. Okay. 3. Okay. So roughly 2:1. 2, and most of them are undecided. Okay, great. So let's try to solve it. Let's see what it does. And yes, it solves it. It solves it. It solves it. In fact, you can take it to the other site also, and it will solve it. Okay. And it should solve it. Okay, so the reason it can still solve it is because the actual symbols are not important, the adjacencies are important. So this is just a demo, this is not the actual presentation. The actual presentation starts now. And let's put this in presentation mode.
This is the one.
Oh.
Oh, yeah. So in case someone doesn't know much about the Indus Valley Civilization, I'll just spend a minute on it. I don't want to spend too much time on it because there's enough information out there, including my other videos, which talks about it. Indus Valley was the largest civilization among the ancient civilizations. It was bigger than all other civilizations combined, except China. ASI has excavated over 1,000 sites, and has found many artifacts. It has found a script. It has found many continuities with the current Indian civilization. So to understand the decipherment is essentially a script. A script essentially is a representation of a language. You have to understand first what a language is. And to understand what a language is, you have to understand the human brain itself. Okay. So the human brain at its core abstraction is a symbol processing engine. So when you're born, you are a blank slate, you are tabula rasa, and you learn to associate symbols with their meanings. Symbols for objects, actions, cultural symbols, and in general, certain set of symbols that are strings of sounds which are associated with objects or actions. So this is very simplified, but essentially that's what a language is. It's about essentially nouns and verbs are objects and actions. So the sounds or the concepts are organized in your brain in a certain way. You cannot just think of an object. You have to think of the things that you do with the object, things that are around the object, the relationship of the object to other objects, and and to actions and so on. Similarly with actions, you need to relate them to other things to have meaning and value in actual communication. So let's say I have in this example a cat as an object and eating as a action, as a verb. So you could say cat, with cat, of cat, and so on, ate, eating, to eat, and so on. But those are a lot of words, those are a lot of symbols. You could compact them and use different sets of symbols to transmit the same meaning. It's just a matter of agreement. If I and you agree that cat is CAT, but to say cats, instead of adding another symbol, we just make it CAF, which is a calf. So as long as we agree, the meaning is transmitted. Same thing with actions. We can just have different strings of phonemes that transmit the same amount of information. The problem is such a language is, although it's optimized for symbol space, the amount of symbols we use, it is not optimized for the human brain, because the human brain optimizes language for cognitive load. Okay, so cognitive load means that when you learn about something, when you want to speak about something, and when you want to add on new knowledge, you want that load to be as small as possible. So in this particular matrix that you see, it's just a representation of how you have two small sets of concepts that you can combine into an exploding large set of words. So if I have a root word like I have a thing, I can add a plural affix, I can add a locative affix, I can add an action, and I could explode it very easily while retaining a small set of concepts. And some of you who are familiar with Ashtadhyayi, you may know that Ashtadhyayi with 2000 roots and 4000 rules can produce billions and billions of words. Okay, so that's essentially the same concept. That shows Panini kind of knew how language worked and how it could be expressed compactly as a small set of concepts. So one of the other good things about this is when a new concept is added, you only have to add it to that particular place. So for example, when in 1996 or 7, when the word Google was added, no one had to go around telling people the gerund, the present participle is googling. People knew this because they knew the ing suffix could be added to a verb to create that. Okay, so you don't have to give the full set of every possible. You don't have to. The whole world doesn't have to come to an agreement on what all the symbols are when they create a new when they add a new concept. So let's try this. But the difference between the symbol efficiency and the cognitive efficiency, that difference is called redundancy. Okay, so I want to try this experiment. So there is this word. It's a 8-letter word, and you can see the first 4 letters. And I want you guys to guess what it is. If anybody has a guess, raise your hand. A lot of people have a guess. Okay, great. Let's ask someone in the front desk. What do you think the word is?
Together.
Together. How many of you thought it was together? Raise your hand. Is there anyone who thought it was not together but some other word? No. That is because the rest of the letters are redundant. You already knew from these 4 that this is the only word possible. Okay, so that is an illustration of redundancy in language. Now, because of redundancy, we can do things like compression. So I could take that previous word, and when I see that sequence, I could put a little code there on the last letter, and that stands for this particular string, and I can compress the. This is an arbitrary code, by the way. It has no special meaning. That you can expand it to this particular value. So this is how you can compress large amounts of text, because language has redundancy. It's optimized for cognitive load. It's not optimized for symbols. Okay, so this is one of the few slides where there's stuff to read. You don't have to read it. I'm going to explain it to you. So redundancy is the difference between the actual encoding and the optimal encoding. So optimal encoding is essentially what is good for symbols. Actual encoding is what is good for humans. And that difference represents the upper limit of compression by a general algorithm, like Lempel-Zev, the ones you find in gzip and so on. Okay, there are specialized compressors that can do a lot more, but we're talking about the general compression. And how much can you compress? You may have noticed that if you have text files in any language, they are compressed to about the same thing. That is because most natural languages have almost the same redundancy. It's about 70%. Okay, because and there are reasons for it. I have a different paper which kind of tries to work out the optimal redundancy of natural languages, but this was this can be experimentally verified by asking people to guess the next letter. So just like you guessed together, pretty much the whole room gets the same word, which shows you that at least in that word, half the word is redundant. So coming back to the structure of languages, we had going and so on. Languages have what's called morphology. Morpheme is just a indivisible unit of a word, a part of a word. And in general, you may have heard of root of a word, you may have heard of suffixes, affixes, and so on. So among languages, there are different kinds of morphologies. One is called agglutinative. This is the most numerous. So Dravidian languages are agglutinative. Japanese is agglutinative. Sumerian, Elamite, many Uralic languages. Pretty much, you can consider this as the default state of languages, default morphology of languages. So essentially, in an agglutinative language, the affixes are regular. Regular means that there is only one affix for a particular concept. So there's one for plural, there's one for gender, there's one for locative, and so on. And they come in a very specific order. So it is very easy to parse. Like if you're a computer person, you know that after this particular root, there can only be this affix or what's next in the list. So you can abstract it as kind of a matrix multiplication where you have the root and you have different affixes, and to give an example, if you have the word our, which meaning him, you can add a plural affix, it will become our ru, and then you can add a locative affix, which make it our ali, and you cannot reorder it. So our lira is not a word. Okay, so that order is fixed not just for Dravidian; it's fixed for all agglutinative languages. It's a fixed thing. It was proposed by a linguist named Singh some decades ago. So it's very well known feature of agglutinative languages. On the other hand, there are fusional languages, which is North Indian languages, Sanskrit, Middle Eastern languages like Arabic, Hebrew. These are Semitic languages. These are fusional. In a fusional, what happens is those affixes that were regular, that were separate, they're all fused into one affix. So, for example, in Sanskrit, you have for ablative case, you have Ramat, Ramabhyam, Ramabhya. So it has, it has nothing. You cannot deduce one from the other. Okay. So it's essentially you take all the concepts, you create a key out of them, and you look up what is the affix for it. And the root class also matters. So like Rama is different from some other any root that ends in a different letter, right? If it ends in a vowel U, it has different sort of affixes and so on. So the last one, this is for completion, is something called analytical. English and East Asian languages are, they don't have affixes. They don't have a lot of affixes. And what matters is word order. Man bites dog and dog bites man are completely different. Whereas in Sanskrit, it's the same thing. Ramaha, phalam, kadati, kadati, phalam, Ramaha, phalam, Ramaha, kadati, they all mean the exact same thing. Okay. So the only thing we have to keep in mind is that just because a language has a particular morphology is not any kind of proof that it belongs to a particular language family. There are, English is analytical, but it's in the group of Indo-European, which is mostly a fusional morphology, and Estonian from agglutinative is slowly becoming fusion, like showing fusional signs and so on. So at least the thinking right now. By the way, all of this is just a lot of linguistics is just hypotheses, and because there's such long spaces that no one has really seen anything. But the idea is that languages begin agglutinative, they become fusional, then they become analytical, and then they go back to agglutinative, and that's some kind of cycle. Okay. So now you kind of have a understanding of how languages work. Let's now talk about script. So language is primarily, when you say language, you're really talking about the auditory communication. It's the auditory channel. And before recording, you could not transfer sound across time or across space. So you had to put it in writing, you had to put it in some kind of visual form and communicate it to a different person. So that is the beginning of writing. Okay. So initially, the idea is that writing started with pre-writing. So traders would mark their pots and pans with the contents of that, for trade. They would mark a fish or grain or so on, and eventually that became a kind of writing. So they would start using those symbols to mean something that sounds similar, or then eventually they would take the first syllable to create a script out of it. So of these, there are different kinds of scripts. Logographic is the pictures, but mostly the useful things we have are what's called logosyllabic. So there is not only words, the signs mean words, there are also some indications about the syllabic value of that word. So Chinese, Egyptian are logosyllabic. Syllabic eventually is essentially a standardization where you start using the symbols to mean a syllable, a consonant and a vowel, or vowel and a consonant, and so on. Linear B is one of the ancient syllabic scripts. Japanese hiragana is also a syllabic script that is in use today. Abjads are a script which doesn't really have vowels. I mean, theoretically they do because you have the and a and so on. Today you also have dots and you have a little more leeway, but the original abjads did not have vowels. And as long as there are no short vowel distinctions, it's a perfectly fine script for such languages. Alphabetic is, you know what it is, we use it for English. You have symbols that represent consonants and vowels. Abugida is a variant of alphabetic where there is a default vowel with every consonant, unless it's overridden with a diacritic or by putting a vowel symbol next to it, after it. So you can just consider alphabetic has a default vowel of virama, which is no vowel, and abugida has a default vowel of vowel. Okay. So Shannon in his 1945-1948 papers, he described language as a Markov process. And for those who are not familiar, Markov process is simply a graph which describes the state changes and the probabilities of the state changes. And it's just memoryless, so that it doesn't depend on the entire history, it just depends on where it is now and the probability of the next transition. The loops you see are because of suffixes. You have ing ending for many verbs, you have es for plural and so on. So they will all converge and create loops. The Markov process, although in this example it was a synthetic language, it's a language for experimental purposes, it's a simple one that's created. But you can do that for real languages as well. It is just that it will be so large that you need special software to create and export it. But here we can show you a small subset of it. So this is, for example, Sanskrit, and from the start, from 0, there's a 6% chance that the first symbol is k, not k the syllable, k just the simple consonant. And you can just follow the chain, and as you see, as the word gets closer and closer to completion, the probability increases because the number of choices, you run out of choices, that are just words. You can collapse some of the branches together and you can create a Markov process with the script itself, with the syllable itself, and you would have slightly different probabilities. It is like you're jumping 2 arrows in the previous graph here, and you are also combining, for example, your Mahaprana, Apaprana, like aspirated, unaspirated into one node. So depending on your script style, you can create a Markov process if you wish. So this again is an illustration of why Markov processes are unique, because the probabilities are unique to each language. You cannot really take words, you cannot trace a graph path from one and impose it on the other. You can do it for short words, you cannot do it for long words, and you cannot do it for many words. So this is, because of something called phonotactics. Every language has restrictions on what can follow what sound. And when you cannot, that creates a pattern of graph that is unique to that language, and otherwise it would be a fully connected graph. Okay. So one of the paths, if you take each individual path that describes a word and you just lay it out, that it shows the adjacencies and the commonalities of symbols in that particular word. Shannon calls these residue classes. So remember, in that demo we had, we scrambled the scramble thing multiple times, but it was able to solve it because the actual symbol, the final symbol doesn't matter. What really matters is the adjacencies. That is what is used to solve it. So in this example we have papaya, which is a word which has these commonalities, which it has 3 A's that essentially are in the even position, and in the odd position you have the P's repeat. So this is a very unique pattern, and if you search in the dictionary for this pattern, you're going to get only these matches. So with this you would get, if there was a script, you would get these values. So there are other words like this millennium and so on, eel, they all will give you value of the symbols representing those sounds. Now what if there is no such single word? What if those words are not used in your inscriptions? You can still get it with multiple words, as we show on the right side here. Here you have A, S, and P in different combinations, and you get a more complex residue class. So you can keep adding words to create the residue class until it becomes unique and big enough that there's only one value for that set of symbols. So you can always solve it. There is no magic inscription. There is no, if I didn't have this inscription, I couldn't solve it. It doesn't exist. You can always solve it if you have sufficient amount of text. And with computers, this is trivial. Okay. So in this case, we have got an A, S, and P. Now, how do you get it? You can, of course, search for it manually. I guess in the old days before computers, but I was not going to do that because we have computers. And you can search them very easily through something called regular expressions. So you see in the word, above the word papaya are written the unknown symbols. Actually they are Greek, so just so that you can mentally can picture what it is. But to search for them in the dictionary, I would use that regular expression above, which is a dot in parenthesis, which is a captcha group, which says, hey, remember the letter at this particular position. Okay, and that for every word that would be that letter. And I do that again. Now it's the second word, it's the second capture group. And once I have captured them, I can refer to them with this \1/2. And that after that there's a dot, which means I don't care what this is because it doesn't repeat. It's not part of the residue. It's not connected to any other member of the residue class. And again, after that I have the \2, which is the second member. So this only gives one result, which is papaya, and just using a regular expression and a dictionary, I have the value of 3 letters. Okay. So once you get 1 or 2 starting letters, you can just continue the process. So in the example here, I have A, S, and T from that complex residue class. And if I find 3 inscriptions that have this unknown symbol, which I put it as question mark here, and the adjacent to these other letters, if I look at the regular expression for any 3-letter word that has A and P as the second and third position, I get a bunch of words. For PAS and followed by an unknown, the same symbol, I get these 2. And similarly for the last one, I don't get those other 2. What is the common letter in that position? It is T. So I have now added one more symbol to I've solved one symbol just by doing this. This is how the dictionary method works, which you saw on the website. It is public, it's well known, it's been around for hundreds of years. And in websites or through regular expressions, it's been around for at least 20 years. So none of this is my invention. I'm just explaining the math to you guys, okay? So the question is, now you have this method that you have seen it work on the website that I have described to you. Can it be applied to the Indus script? What is the Indus script? How do we go about it? So this is where my work starts. Okay. So the first signs of the script we see in 4000 BCE as graffiti on potsherds in a place called Balakot in Balochistan. It's on the coast. And it's from 4000 BCE. Those signs, some of them are abstracted, so you can see in the second row from the first sign here is the jar sign. The first symbol in the last row is the arrow sign, that's abstracted. And you have the unabstracted arrow on the second row there as the third symbol. So you have both the abstracted and unabstracted versions. So we don't know at this point, there's not enough samples, there's There's not even entire inscription, so we have no idea if this was pre-writing or anything at that stage. Okay. So, but by the time the Harappan civilization becomes mature, the script is fairly standardized. It's everywhere. You have the same inscriptions in multiple sites. You have the same iconography. It is a fully developed script. But the earliest pieces have only 71 symbols. Okay. The inscriptions mostly they are on seals, and they're about this big, 3 by 3 centimeter or 4 by 4 centimeter. So there is a deficit of space. So they have to be very judicious on how to use the space. You see writing on personal items and implements like bangles and so on, which may suggest that the general public was literate and not just some kind of special elite class. We also have post-fired inscriptions, which means, so when you have a pot and you write it first and then bake it, it's generally there's a specialist class that reads and writes. But if the pot is already made and it's already been circulated and someone writes on it, it's generally a sign that the general public is literate. So we have that in Indus Valley Civilization. So about 17% of the inscriptions have repeating characters. So you may have seen Dollavira sign has like 3 or 4 those beans, and the Pashupati seed has 2 of the scraps and so on. So there's plenty of repetitions which indicates that it's not a logographic script. Okay. So in my paper I have the math for that as well. I just won't go into a lot of things here. So what does script like? The script looks like this. Just have a look and just try to get a sense of what you sense from it, what you get from it. So, does it look like writing? Who thinks it looks like writing? Raise your hands. Some unknown script. Nobody? Oh, 3, 4? Okay. Who thinks it's just random symbols with no value? Nobody. Okay, so most people are undecided. Right, so the question is it writing? And there's been some studies that showed it is writing, and it has the entropy of writing. So, and there's also a study that showed that the direction of writing is right to left. You would not get this if it was not writing. So how do you know it's right to left? Well, you can see that scene with the unicorn, that they started writing with complete confidence, with proper spacing and characters of the same height. And then they suddenly realized they're running out of space because of the head of the animal. So they just started sliding into they started crowding in that space, and that generally means 2 things. They're writing from right to left, and it is not logographic. It's not 1 word per symbol, because then you would know I'm writing 4 words, I need this many symbols. I am writing 6 words, I need this much space. But when it's a word that doesn't have a 1-to-1 correspondence to the length, you don't have an idea. So when you write a word in English, for example, when you say something like through, it is short in your brain, but it has so many letters. So that is when you get out of space. So this is one of the signs of that. And it's not just on the seals; it's also on inscribed copper objects, on bas-relief tablets. Things which are not impressions but actual things that they made directly. They all exhibit these features. And in the center, there's a Gini coefficient from a study that shows that Indus script is right to left, regardless of the script type. Even if it's logo, syllabic, or whatever, it has to be from right to left. So Yajnadevam looked at Yajnadevam is an epigrapher who's done a lot of work on Indus script and other South Indian epigraphy. He's read a lot of inscriptions on caves in Sri Lanka, Tamil Nadu, and so on, mostly in South India. And he noticed that there are inscriptions that are the same on 1 and 2 lines, and that they could only be read this way if it's from right to left. So we mentioned that there's only 71 signs in the earliest first period. What does that mean? So a logographic script would require a huge signary, 1,000 or so minimum. I think the smallest is Luwian hieroglyphs with something like 600, 700. And the Chinese, as you know, has about 40,000 something symbols, even more if you consider the old text. So it is unlikely that a script that has so few symbols and so many repetitions is anything other than syllabic or alphabetic or some kind of segment of abugida or something like this. So how many signs are there? I mean, when you look at the signs, there looks like some signs have evolved, they have been abstracted over time, and they have been simplified. There are the elaborate types, but there are obviously things that have been kind of abstracted away. Now, think of what abstraction means. If you and I agree that dog stands for D, we could draw the dog standing, sitting, sleeping, eating. You would still know it's a dog. So that's quite simple. Think of emojis today. If I say smiling face or whatever, you want different platforms, Android, iPhone, some other tablet, some vending machine, it all looks different, but you know that this emoji means this, right? Even other objects like pistol order, everyone draws it in a different way. But in your mind, you know immediately this is what it stands for, right? So for that to get abstracted, so as long as it's a concrete representation, it doesn't take long for you to recognize it. But if it has to be abstracted, that abstraction has to flow around enough to create enough network effect that people will start using it as an abstraction. So it takes hundreds of years to create these abstract versions of signs. Okay. So we see these versions. Some of them could be just stylistic variations. Some of them are actual abstractions. Like that leaf is definitely an abstraction. If you look at the end, it's hard to guess it unless you have gone through these other intermediate stages. So the way we figure out whether a sign is abstraction or a distinct sign is we can do that using the same dictionary method. You can simply try to see if there are words that generate common values. So in the upper example here, although those two signs look similar, they don't have any common for that particular position in the inscriptions. You don't get any common values. So you can be confident that they're distinct signs, that they're not stylistic variations. Whereas in the second set there, although they look somewhat different, you can see that R is common in both rows. So therefore they are allographs. So this is how you can figure out whether the signs are the same or not. And this is better than just visually looking at something and saying, well, it looks different to me. So because that in an unknown script, if I give you, let's say the Latin script, the English script is unknown to you. If you look at capital A and small a, you may think they're different, right? But someone else may say, if I write it like this or like that. So you're going to disagree, and the only way you can confidently make that determination if you already know the values. So once you find the values, you can make a determination. So let us go through the derivation process and find the sign values. So this derivation that I have in the paper is for you to follow easily, one by one, and follow along and be convinced that these are the values and those are the actual words which are in the dictionaries. You can check and so on. In addition to this, as a decipherer, I have to do many more checks, okay, many different combinations, derive the same sign from many different sets of words and so on. Okay, but for the sake of explanation, the jar sign, because it can represent an, and it occurs at the end of many inscriptions, it probably is a marker of a case marker, like a accusative So we give the value unto it, and then using just that sign and finding inscriptions with only one additional sign, we derive the next value, which is the stick sign and its So we can keep doing that until we get all the values. And once we get the values, we can arrange it in the Varnamala, the Indian alphabet. And what do we see? We see that they, we can try to reconstruct the sign name, and it's very straightforward. You look in the dictionary for anything starting with that value that looks somewhat like this picture, and what you get is you get words that are very close. It's as if someone said it orally, transmitted the value, and it got slightly corrupted, and that resulted in an adjacency. So this is essentially the this is how the values were derived and the names were reconstructed, and this is how we know that because of the closeness of the values, we can guess that this is essentially a correct decipherment. So the values are so close that you can see it is it can easily be easily from mispronunciation or something like that, it could be transmitted. For Shasha Saha, the values are the same, and this kind of indicates that in those days there were multiple dialects. So if you guys may be aware, in Prakrit, Shasha Saha kind of keeps changing around. Saha is interchangeable in many Indo-Aryan dialects, and in Panini, Shasha Saha is the same group. Okay. So, so the question is, why are there so many symbols? Why didn't they standardize it? In many scripts there were multiple symbols, and in some they kept it that way for aesthetic reasons. English, for example, has 4 or 5 F sounds for F, FF, LF, HF. These are all GH. These are all F sounds. So the question is, why didn't they standardize it? If they had it for so long, why didn't they pick the simplest and create a standard alphabet? Yeah, you can understand, right? There was so many different sites which independently sprung. Somebody goes, memorizes the value of the symbols, he transmits it there, they hear it slightly differently. Different symbols are created, but people can kind of figure out just like different emojis. But over the mature Harappan period, when all of this administrative machine was going on, why didn't they standardize it? Well, eventually they did standardize it, and this is what happens when you pick the most simplest symbols and arrange it. You get essentially the Brahmi script. Okay, so Brahmi is nothing but standardized in the script for the same values. Okay, so that is the decipherment. Now, after this, there is a little bit of, so say deciphering the Indus script is not the big issue, because there are 100 decipherments, and probably there's one more as I just gave this presentation here. The hard part is proving that this is the correct decipherment. Every previous decipherment is false, and every future decipherment is false. And to do it in a way that you can trace the decipherment, you're not going to find this trace for any other decipherment. You just have assigned values. The trace that you can follow along and work it out yourself, and a mathematical proof that this is the only one. So I can go through that and then do questions, or should we take a break and ask have questions here as well?
I think let's go through.
Let's go through. So there's some math here. I understand that there's mixed crowd here. Some people are very comfortable with math, and some people are not. And professor asked me to give
you can get into the mathematical details. There's a good amount of representation
I know.
Computer science and
Yes. So professor asked me to give you guys a 2-minute break. So if you want to pray or get a hot cup of hot tea or hot coffee to drink, Anyway, so let's go ahead.
No, I think the tea is there, so I think maybe we can pick up our teas to do some math.
So I'm going to start. So essentially, everything so by the end of this you'll be convinced that should we pause here for the thing or not?
No, before this process is done, summarize it actually, what exactly is now discovered, shown as gradability is not actually.
Right. So we have deciphered all the symbols in the Indus script. You can read the entire Indus corpus, and we have read about 40% of the Indus corpus. We are on way to read all of it.
I think we can continue while we go, because we have a hard stop at 4 where this room is booked by the next person.
Right.
So,
Okay, that's mentioned.
So that we will also have time for questions at the end.
Right. So, so to understand the math of the proof, we have to understand what is information and whether information can be measured. So everything I'm going to say, except a couple of things, are from Shannon's 1945 paper. It's the most cited paper in mathematics, at least in cryptography. It has close to 75,000 citations. Okay, and only a couple of minor things are mine. So if I make a mistake, it's not Shannon's fault. I'm just optimizing for narrative purposes. So information is essentially when something is certain, there's no information. If I say it is daytime now, you didn't get any new information. When everything is equal probability, then you don't have, you have the maximum uncertainty. Okay, and when you should be able to sum information from different events together. So these are the criteria for information, and minus log of the probability has all of these properties. So that was chosen as information. And entropy is the expectation function of information. So what is the expectation? It's just probability times the actual value. So for a coin toss, if you have 0 and 1 on a coin, you toss it a number of times, you take the average, you expect it to go 0.5. If you toss a die, you expect it to be 3.5. Okay. So entropy is the same thing for information. It's just the sum of all the probabilities times the log of the probability. So this is an example of a fair coin and an unfair coin. So if you have a fair coin, the entropy is maximum. It is essentially one bit of information. It's either true or false, 0 or 1. The number of bits is 1. There is just one alternation. But if it's an unfair coin, which lands heads 3 or 4 times, then the actual entropy you get is actually less than 1. So this is kind of important when we want to prove the correctness of the decipherment. Plain text and ciphertext. Plain text is nothing but it's plain. You can read it. So it's a message in a known symbol set. So this, for example, is in plain text. If I write it in an unknown script, it's ciphertext. Cipher means it's hidden, so you can't read through it. The alphabet or signary. Signary is just a set of signs. Alphabet is the sign of alphabets. You can think of them as equivalent. It's just a set of glyphs. So you have plain text alphabet and ciphertext alphabet. And when you decipher something, the assignments you create for those ciphertext symbols is called a key. Okay. So when I say key, that's what we're talking about. What has been assigned. Key space is the number of possible keys. So what does that mean? So let's see. If I have if I can open a lock, but I have to press one button, just one button, just once, and it's all digits. How many? The keypad only has digits. What is the number of possible keys? Anybody? 0 to 9. How many are there? 10. Okay. And if I have to press it twice, if I press two numbers, how many combinations are there? 100. Okay. If I have to do it n times, how many are there? 10 power n. Okay. So you guys have protected the reputation of IIT by answering this question. So, all correct. So now if it's A to Z, then what happens? How much is it for 26 to the power n? Okay. Now if it's not A to Z but it's an unknown alphabet, if it's an unknown sign with P keys, with P signs, the plain text is P, but the number of things in, how much is it? Sorry, what? P to the power C, yes, that's correct. P to the power n or C, yeah. So that's good. So you guys understand what key space is, that makes it very easy. And now we have to talk about rate of language. So what is the rate? Rate is essentially measuring the number of, the rate at which symbols can be produced or information can be produced. Okay. For a system, for a channel, for a alphabet, for a. So if I ask, are you over the age of 18? There's nobody under the age of 18 here, I hope. Okay. If I ask if you're over the age of 18, the answer can be yes or no. So that is one bit of information. Yes, no, because it's 2 to the power 1. There are two answers. There's 2 to the power 1. That's one bit. If I ask what day of the week it is right now, that's 7 answers. So almost 8. 8 would be 2 to the power 3. That's 3 bits. It's slightly less than 3. Okay. So in other words, if there are n possible values, the rate is log to the base 2 of n. So if the script has p symbols, the rate is log to the base 2 of p. Now that rate is called so all these symbols are Shannon's, except the last 2 lines are mine. I'll explain what it is. Very simple. The rate of what he calls the max rate is the rate at which you can produce symbols and you can pack in information. If there are no rules about syntax and phonotactics and grammar and prepositions and all of that. Okay. If you can just compact everything into symbols, that's what we saw in the previous page, is log 2 to the base p. So log p to the base 2. And if you account for all the meaning, if you have to respect the prepositions, if you have to respect the syntax, the grammar and everything, that is R. Okay. So R0 is essentially no structure. R1 is structure for 2 adjacent symbols. R2 is for 3 and so on. And R is same as R infinity. All the structure is taken into consideration. So the difference between these two rates is called the redundancy. Makes sense? I can produce so many symbols out of which only so much is information. The remainder is redundancy. R by R0, which is the information by the total symbols, is called relative redundancy. It's also an estimate of, or it's a theoretical limit of compression. You cannot compress beyond this without getting into lossy compression. Makes sense, right? R is all the information, R0 is all the symbol space. So if that is the max structure, max compression, that ratio, what happens if you remove that ratio from 1? You get the redundancy of the language itself. Okay, so I've given the symbol rho to it. I saw this, all of the symbols I saw on different papers, none of these are mine. So the last two lines are mine. All I've done is in the first line I've multiplied by R0, and the second line I've substituted the value of D and log to P to get the redundancy in terms of the redundancy of the rate in terms of the redundancy of the language. Okay. So now let's talk about introducing uncertainty. So this quote is straight from Shannon. Uncertainty is the amount of different ways you can read. You can just add, or you can say, oh, maybe this word is this. Oh no, it's this. So the number of possibilities of what a word could be, it can only be introduced in the key, because the inscriptions are the inscriptions, right? The plain text you can't alter it. You can only just change the key and try to get different readings as possible. So it has to be in the key. So, so what is the amount of redundancy in a text of length L? So if it's for 1 it is D, for L it's LD. Simple multiplication, right? Now all the information in a key space is, the notation for that is just K between vertical bars. If the statistical structure read is greater than all the information in the key, so if you assume that everything in the key is redundancy that's been added, but you have read more than that, you have read more redundancy than that, not information, more redundancy than that. You have also read the other stuff also, but you have read more redundancy than in the whole key space, then that cannot have come from anywhere else except from the inscriptions, right? Except from the actual from the cipher text. So at that particular length, you have reached a point where there is only one possible reading. That's called the unitary distance. It's simple as that. There's a more mathematical, cleaner way to express this in terms of number of spurious keys. You can set it to 0 and all of that. But I'm just hoping this is more understandable to a general audience. This formula, by the way, is also in Shannon. If you don't understand it, that's fine. You can look it up later. And none of these I'm deriving, by the way, right here on the spot. So now let's talk about some of the other decipherments. So people ask me, hey, why is your decipherment right? What about, Mr. So and so? His decipherment says, all these big things. It says 4 Vedas are great. It says, Ramayana. It says this and that. It says Murugan. It says metal, all stuff. And it sounds impressive. There's all this cool stuff in there. And why is your stuff has the same? Your stuff has different stuff. So why is yours correct or wrong? And I'm going to try to demo why. So I want you guys to look at the symbol and tell me what it could represent. Okay? There's no wrong answers. Don't be shy. Please participate. Why don't we start with you, sir? What do you think this looks like? Come on, someone must have imagination here.
B.
A bee, very good.
Butterfly.
Butterfly.
Family.
Family.
Eyes.
Eyes. Anybody in the back?
Chariot.
Chariot. Okay, that's nice. Okay, what is?
Grains.
Grains. Okay. So every time I ask this question, I have heard things that I have not heard before. Okay, I don't think you're afraid like this. So the point I'm trying to make here is that by looking at something, it looks like a different thing to different people. So the claim that I've looked at it, I've stared at it for 2 hours, and it spoke to me, and I know for sure it is this or the other, is not a method. It's not a verifiable method. It's not a reproducible method. It is just an assumption. It is just a feeling. It's not decipherment. Okay. And these are actual readings by 2 decipherers. The first is Oscar Parpola. So he decided that those things are bangles, the 2 circles. And there's another sign that is just 3 lines, 1 line between 2 short lines. And he said it's a herb. And then he found this combination where there's herb and bangles. And herb bangles doesn't mean anything. So then he said, well, actually it's pregnancy bangles, and there's this tradition in Tamil Nadu where they, during pregnancy they do bangles and stuff. So what is happening here is, as he is reading more inscription, he is adding more key. Now he has added new values to this particular arrangement. Okay. Now imagine what happens if for every arrangement, every permutation, you have a new meaning. How many? What is the size of that? Does anyone recall?
No.
Sorry, what? LD? No. It is for n symbols, it's n factorial times e. Okay. And n factorial for 400 symbols is what? It is much larger than the number of atoms in this universe. And if you take every atom as a universe and you go into that and keep doing that thousands of times, still you won't be able to count it. So it's essentially infinity for all practical purposes, infinite number of keys. So the second one is from, so even if you do that, you will run out of a time when things will start being meaningless anyway. So second one is from Yajnadevam. He claimed that this fourth sign with the number 2 is a ruler in one inscription, and in another inscription he said this thing with this person with 2 jars is jar bearer, and in some other sign, that bird thing, he called it a chicken. But there is another inscription which you'll be forced to read as ruler, chicken, jar bearer, which is fairly meaningless. I mean, I've tried to put meaning into that, but unless it's some dish on some Hyderabadi menu, I don't know what it is. But that's what happens. You'll be forced to create new narrative and new meanings and just keep generating the key to read it. So what are you doing? You're reading the key, you're not reading the inscription. Okay. So that is what Shannon meant. You can only introduce as much uncertainty as the key. I mean, that is technical language, but this is what it means. So, in terms of mathematics, the unicity distance of a logographic system is infinity because the key space is unbounded. There is nothing to prevent me from calling that symbol anything I want. I mean, out of a sense of my consistency with my own imagination, I may want it to look like wheels or bangles or something, but nothing prevents me from calling it baby or stone or anything, really nuts, TV. What is to prevent me? Nothing. So that the symbol space, the key space of a logographic system is unbounded, and this is why for a logographic system you need a Rosetta Stone. Because what a Rosetta Stone does is it limits your options. So you say, I, King Ramses, in the unknown script you should expect something like that. Maybe there's a little preposition here, there's a little word order here, but it limits your choices so that you have a unicity distance. Without that, it's essentially infinity. Now there are some other decipherments where the language is kind of sounds something like some Hindi or some old Prakrit or something, but it's not a real language. You will have words like Shivaku or something like this, and you are required to imagine that it is Shiva and there's some kind of unknown affix there. So when the number of incorrect words are 0, then here the D is 0. So that's what the equation at the bottom is. If the key space is unbounded or the number of invalid words is 0, then the unicity distance is infinite. So every other decipherment so far falls into one of these two camps. So they all have a unicity distance of infinity, and they are all therefore dubious. Okay, so what about my decipherment? What is the unicity distance for your decipherment? So going by this, this is just I'm deriving the formula here. The values that I derived in the previous slides, I'm just putting it here. The K is log to PC, we saw that earlier. D is row log to PC, we saw that earlier, derived. So unity distance is turns out to be C by row. Now, and row we know for most languages 0.7. For Sanskrit, there's a very specific paper that has shown it can be compressed to 0.7. So that is essentially the value. C.
Excuse me. So what is C? Can you remind me again?
C is the number of symbols in the ciphertext. So it has to be adjusted. So if you are reusing the symbol for multiple alphabets, you have to count there. You have to increase the count. If you are, if it's essentially it's very simple. If you don't have any equivocation, you don't have any choice, then those symbols don't count. If you have a choice, then that choice has to be factored in. So this roughly comes to around 400 something unity distance for me. So this is just a different. Okay, so that is essentially it, and that is why my decipherment is the only one that has a unity distance as a mathematical proof of correctness. Before you ask questions, there are some common questions that's asked everywhere. I'm just gonna proactively answer it so that we can go for more interesting questions. So one of the questions I was asked was, does the unity distance work for like a single long inscriptions, or can it work for multiple short inscriptions? Yes, it does work, and the reason is, so the question is asked also as a different way that, hey, if it's different inscriptions, how can it be the same cryptogram? So you have to understand, cryptogram is a function, it's a transformer, okay? And anything you push in it, anything is a stream that comes out, it comes out encrypted. So if I take a encrypted text, give it in one piece, or I give it to you piece by piece, and at the end you have the same full set, is it going to make a difference on whether you can solve it or not? No, it's not going to, because you have the same adjacencies, you have the same text, and it works for your newspapers also. You can try it. You can try, cutting pieces of it, and it will still solve it. Okay. Okay. So there are a bunch of questions about a script, like why does the script have multiple allographs? Why does the signs for sure is reused, and so on. There are allographs because it's a Bronze Age script. So you guys are in 2024, soon going to 2025. You have 4,000, 5,000 years of head start on what is a good script. But for them, it was a big technology. And multiple allographs exist in many scripts. So this is a Mayan script. There are 10 values for oo, the sound oo. Okay, they have, and again, English has multiple allographs. Japanese has, 3 allographs for many sounds, because they have katakana, hiragana, and kanji for some sounds. So this is very normal that there are multiple allographs even today in modern scripts. The signs for Shashasaha, they, I think, represent the existence of multiple Indo-Aryan dialects, because we see during the Gupta era and even during the Ashoka inscriptions, they would interchange sa and sha, ka, like the unaspirated, aspirated. They would just interchange it because in Prakrit, Sena becomes Shena. So they would read it that way. They would write it interchangeably, basically. Okay, so there's one more question. You used words from Mahabharata and so on. You don't know if those words existed. Can you decipher it using only the old words? Yes, you can. It's just that remember I showed you the complex graph, the residue class. I would have to do that many times, and for a user to follow it neatly one by one is a lot easier. And remember, anyone can. I shouldn't say anyone can, because no one has deciphered it 100 years. But deciphering is not the hard part. The hard part is having everyone, like ordinary people, follow it step by step and understand it and accept it, not just experts. Okay, so it's just the linear flow makes it very simpler. So that's why I've used those words. The other question is, why are you using Paninian grammar? Panini was around 600 BCE. This is from 2300 BCE. Blah blah blah, things of that nature. So Paninian grammar is a subset. All grammars are subsets of existing dialects. Okay, and Paninian grammar covers some 90% of Vedic grammar, right? Maybe more. It leaves out a few things. Late Lakarite leaves out the separated particle from the verb. It leaves out, and very few things. Some roots, some 200 roots, it leaves out. But so that is not a problem for us. We know that we are fairly confident that the noun cases, the conjugation, they're all the same. And occasionally, yes, we have found in inscriptions, we have found late Lakar. We have found the older inscriptions, but we don't have Aindra grammar, we don't have any of the old grammar. So this is such a good approximation that we are fine doing it. So that's basically that's the end of the show. We can open it up for questions. Yeah, that's behind you.
Allographs. My question is, if this is great work, and I'm curious what the implications are on the current, especially sort of Western international understanding of history of language, and so if all this is correct, and it certainly looks correct, what are the implications?
Yeah, I think that's a burning question for a lot of people in the index space and also the linguistic space. So the key, you have to understand what linguistics is, how it developed, and what exactly the linguistic relationship represents. So it was observed that Sanskrit, Greek, and Latin are very close, and some other European languages are also relatively close. And what could be the reason for this? And they came to an axiomatic model that these languages had a common origin and they related to each other as a tree. Now you have to understand what an axiomatic model means. It means somebody just made it up. Somebody just assumed, and it's not a bad thing. There are a lot of useful things that are axiomatic: geometry, astrology. Many of these, there are many things in like your economic theory. These are just axioms. And just because there are no pentagons in the natural world doesn't mean geometry is useless. So it's an axiomatic model, the purpose of which was to describe the relationships in a way that everyone can commonly talk about and understand. The issue happened when people started saying, well, if it's a tree model, then there's an origin, and then that origin must be somewhere, and then how did it spread, and all of that stuff. So now they have divorced the axiomatic model from its axiomatic rules, and have assumed it's a historic model. And the historic model is made of their dates, not ours, their dates, 1500 BC or 1200 BC Vedas, and some 700 to 900 BC Greek has yielded 4000 BC proto-Indo-European. So this is kind of, if it's axiomatic, then there's no problem. But if you start imagining it's real, then it just doesn't make sense. So what we know, to answer your question, what this means is that Sanskrit, as we know today, or something very similar existed from 3000 BC when we get the first inscriptions, and possibly 4000 BC when we have the script. Okay, that's what it means. So if they want to retain the model, it's very simple. They just have to move the dates back, move it back by another couple of thousand. So there is, so you would have to detach it from this place and time of your, whatever it is, was your favorite time and place. But yeah, it would still work. Anyone else?
Yeah, so
Wait for the mic, please.
So I just continue the previous question. So one way to address that would be to revisit, the linguistic assumptions as well, because every time you have a new branch of science, you develop based on what you know. So if there is new knowledge, then it is probably better sometimes to go back and forth, rather than having everything new fit into everything old. One can probably go see how a common framework can explain both of the things together, rather than the earlier thing, meaning the newer thing always having the burden of explaining or being consistent with the older one. You can probably, can have a consistent theory in which both the things can fit.
I think this is essentially a suggestion, not a question, but let me add to that. I think what you're trying to say in a more polite way is that certain aspects of linguistics is now falsified. And I agree. I actually think that if you guys are aware of the history of the whole linguistic framework of PIE, it was never meant to be a temporal language spoken in a place by certain people. It's just an abstraction to describe relationships. The shift from that abstraction to an assumption that it was real is just has to be discarded, and you just have to go back to the original thing. You can of course try to derive new language trees, and that people do that every day, so it's not anything special.
Thank you. So, how does the gender?
What's the sequence? When can we say that this is deciphered?
When can we say that this decipherment is accepted by
Community.
which community? As the whole world. Well, you are free to accept it now. Okay. So yeah, that's a good question. Scripts are generally accepted very slowly. Like I said, Champollions decipherment, he had to die before it was accepted. I believe linear B took almost like a decade or maybe more. For us, fortunately, the zodiac was, because it as a unitary distance, it was accepted immediately. And I would think under normal circumstances, this would be accepted immediately because it's the same thing, and there is nothing extraordinary or special. Everything in here exists already. The way the symbols work, every single thing already exists in some of the script. So so I would say that if this wasn't for this whole political thing in the universities and in the thing, then it would be accepted immediately. And I think a simple thing could be if experts like you, people who are experts in mathematics, information theory, Sanskrit, just endorse it, it would be very fast. The issue is, in general, people are afraid to endorse because 6 months down the line, someone proves it as false, then you have to retract your endorsement. So people are afraid, and it's the same issue with other decipherments. People are kind of afraid. But if let's say even two mathematicians or two computer scientists say yes, this makes sense, I verified it, it is correct, all the dominance will start falling.
In this particular case, when you say you have deciphered this script and language relationship by some symbols, then you should show actually the paradigmatic equations in terms of nominal symbols and as well as the verbal symbols. Have you built up any paradigm for any of the categories?
I did not understand the question. What exactly?
Okay, you have said that there is a makshika, there is a matsya,
Right.
some nouns you have established. Similarly, you also have probably some verbs you have established, right?
Okay.
Reading the symbols.
Right. No, so
Do you accept that?
think, no, I think you misunderstood. those are reconstructed names of the symbol. Symbol values are, so here for example, so the symbol values in this chart are the verb and the shashasaka. So the only thing here that is a decipherment is the first column and the last column. Between the first and the last column is the reconstruction of the meaning of the symbol. And that, whether I'm right or wrong, is irrelevant because it doesn't change the value of the symbol or it doesn't change the reading or anything.
Now, have you read a sequence, right? You have read a sequence.
I've read the inscription.
Yeah, sequence of symbols, right?
Yes.
Now, in such cases, did you find or did you come across a paradigm? Like, books, something of that sort. Book is a root form, and the books it's a paradigmatic notation.
Right. So you are asking if there are grammatical
Inflectional set.
Right. Yeah, of course. Plenty of it.
Yeah.
So let me actually bring up. I can't share this, right? Right. So the entire So this is the entire repository of the Indus script. 40% is translated, and you will see all grammatical elements. You will see noun cases in the vocative, the nominative. You will see ablative. You will see in conjugation. You will see lot lakara, which is a prayer. You will see lit lakara, which is past tense. You will see all of that. Everything is grammatically correct.
So have you set aside, okay, these are the inflectional endings and these are the roots, and so you can have a set of paradigm that can be defined by this prediction or this kind of decipherment?
So I think you're talking about whether the things
No,
have been glossed.
What I would say,
I understand your question.
Yes.
I am rephrasing it in terms that are kind of linguistic standard so that the audience understands. Okay, the people on the webcam understand. That's called glossing. Glossing of the words. The glossing of the words has been done for the 50 longest inscriptions.
No, I'm not saying the glossing of the words. Glossing, I don't know, at this level I can say glossing, but I would say at least have you discovered in the data some paradigm of a given noun or a given verb?
So when you say paradigm, it's not a standard term. So I don't know, paradigm can mean anything. I don't know what you mean. Linguistically, what's a paradigm? What do you mean?
Some like take an X as the root and ABC it's the suffixes. So XA, XB, XC, I'll take it as a paradigm.
Right, that's not a paradigm. That's the word for that is noun cases. And yes, we have noun
No,
cases.
no. Okay, whatever way you define
Okay,
it.
we have noun cases. We have conjugations.
Yeah, conjugations.
We have conjugations. We have noun cases. We have imperative negatives. We have
No, to that extent, okay, it's
Yeah.
a noun plus cases.
We have all
So
of
that's a paradigm.
Yeah, we have all of
Okay.
it.
Yeah, did you come across that kind of thing?
Yes, everywhere.
Can you show that one?
Okay.
Because that gives us clearly a kind of logical inclination to believe, yes, this
Sure,
is.
sure. So for example here, by the way, all of this is in my paper. The top 50 are completely glossed. Glossed means what you call paradigm is in there. The noun cases, whether it's the 6th vibhakti, 7th vibhakti, whether it's all of that is for every single word has been glossed. Okay. So here, for example, na is dative. It's the 4th of asmat, of the root asmat. Okay. The is dvitiya. It's accusative of Markov. Okay. So you can go through the paper. It has the longest 50. Everything exists. So here, this for example is plural. You can go through all of them. I'm trying to find of conjugation. So for example, see here mama for example is shashti, is possessive of asmat. So you have them all. Every single word of the 50 longest has been glossed fully.
Okay, mama means what is the other one? It's a relative.
Mama anjasmana. Arava mama anjasmana. I suggest, I don't want to spend too much time on the grammatical things. It's all glossed. Please read it. If you have doubts, send an email to me. We can continue the conversation. Let's get one more question.
So, does tokenization make it? Okay. Does tokenization make a difference? Do you tokenize and then do your cryptograms?
Right. So that's a good question. When there are no spaces, you can break the inscription in multiple ways, and there is no meaning-wise, they are all equally valid. Okay. So, for example, if I have leader got in, you can pass it as leader got in, or led or got in, or so on in multiple ways. And there's no reason why one is correct and one is wrong, But overall, if you look at the sum of inscriptions and choose the tokenization that results in consistent themes, that's what I've chosen. And my goal is not to, my goal is just to show this is a meaningful decipherment, and someone else can build on top of this and say this is the actual meaning based on, on their research.
Right. It's another question. So now let us say you run your algorithm as is, the code, everything stays, okay? But I just swap the dictionary, okay? And I swap it with a Tamil dictionary of the Sangam literature.
Yes.
What happens?
Battery 25.
You're going to get maybe one or two signs max, maybe not even one.